problems. You are working on AlGenCan maybe in the last 2 decades. Our first paper concerning theoretical conversion results on AlGenCan is now 10 years old, but we started to work on this a little earlier than that, working on solving subproblems, bound constraint minimization, and so on. And now I would like to present to you what is written in the title, which is improvements in AlGenCan based on theoretical complexity results. We were working in the last few years with some colleagues, I will mention in a moment, in complexity results for unconstrained minimization and for nonlinear programming. We were concerned after working in these complexity results whether they could be used to improve practical performance of algorithms. And this is our attempt of improving the practical performance of our nonlinear programming solver using those complexity results. I will end the presentation showing some numerical experiments with AlGenCan, and I would like to put this in a context. AlGenCan is a viable free software for nonlinear programming, general constraints, smooth problems, and there are not many solvers freely available, open source like AlGenCan. The other one is IPOpt, interior point methods, so a very different approach. I will show you numerical experiments comparing both to put AlGenCan into perspective. And other than IPOpt and AlGenCan, I am not very much aware of other open source solvers. Maybe you know Canitro and SNOpt, and if you would like to use them, you should buy it because they are not freely available. So what we are talking here is about improving the performance of a method that is open source and that you can use if you need. Also, this is a joint work with Mario, but I will, as I said, the theoretical complexity results that gave origin to these improvements were also done in collaboration with Sandra, that is here, and John Lennon and Philippe Tuan. ¿Qué que eu tenho que apertar aqui? Está desligado. So this is the general nonlinear programming problem. We have minimizing objective functions subject to equality constraints, inequality constraints, and bound constraints. And the idea, as I already said, is to improve the practical performance of AlGenCan based on recent results, complexity results. So the schedule of the talk is an example of one of the main advantages of AlGenCan. Maybe you hear from Mario yesterday that we claim every time that AlGenCan has a modularity. And by modularity, we mean that AlGenCan solves, in augmented Lagrangians, you can split the constraints in constraints that will be penalized and constraints that will be kept as constraints in the subproblems. So upper level constraints and lower level constraints. In the context of this talk, lower level constraints will be only bound constraints for simplicity, but most of the results apply to arbitrary upper level constraints and lower level constraints. But in the case of AlGenCan, which is an implementation of an augmented Lagrangian method, the subproblems has as lower level constraints only bound constraints. So in the context of this augmented Lagrangian method, you can use any method to solve the subproblems. Theory is not attached to any kind of a special method for solving the subproblems. Anyone could be used. And in the particular case of this software, the bound constraint minimization solver is an active set strategy. And within this active set strategy, you have phases. So you have some constraints that are fixed, bound constraints that are fixed. So at each iteration, you solve mainly an unconstrained minimization problem, and this unconstrained minimization problem can also be solved by any unconstrained minimization solver. So this is the schedule of the talk. I will start talking about unconstrained minimization. Then using active set strategies, you can plug this unconstrained minimization solver within the context of active set strategies for solving bound constraint minimization problems. And then you can use this bound constraint minimization solver to solve the augmented Lagrangian problems. So you can, in some way, in this direction, improving an unconstrained minimization solver, you improve the practical performance of a method for nonlinear programming problems. So this is the modularity of AlGenCAN, and this is the modularity of the talk as well. I will skip the part in which the unconstrained minimization solver can be used to solve bound constraint minimization problems. In fact, I don't expect you to remember the one that you were here last year, but I talked about that in the last Brainstorm. Not in the I show in the previous workshop how can this be done using a method that possesses complexity results for unconstrained minimization, but that complexity results came from solving quadratic regularized subproblems. And then we put this in the context of bound constraint minimization. In this presentation, I will talk about another unconstrained minimization solver with complexity results. And this other unconstrained minimization solver is based on cubic regularization, so it has the optimal complexity. And in particular, this first part of the talk is one of the attempts of producing a practical algorithm for unconstrained minimization based on complexity results. And the practicality of the approach comes from this what we call mixed factorizations that I will introduce in a moment. After explaining the unconstrained minimization part, I will mention that this can be plugged into the active set strategy, and then we will go to the nonlinear programming. This is the second part of the talk, where I will try to show how these improvements in bound constraint minimization give us improvements in the nonlinear programming framework. So now we start from unconstrained minimization. We need to minimize a smooth function. We already know the optimal complexity results, epsilon to the minus 3/2 for Newton-like method with cubic regularization. However, up to our acknowledge, when you have this kind of method, you need to solve the quadratic model with the cubic regularization term. And to solve this, or you need a very expensive factorization. We say the spectral decomposition is, in this context, an expensive factorization. Or you may need to solve this iteratively, and solving this cubic regularized model iteratively is also expensive. Or maybe in some recent works, you need to compute at least an eigenvalue of the full Hessian. And we consider that it is also expensive. And we are trying to find an alternative to all this stuff. And the alternative means to perform a single cheap factorization per iteration. And by cheap, we mean a factorization as cheap as a Cholesky decomposition. And one other detail is that we are talking about single factorization per successful iteration. This is to stress that in the transition approach, you do one Cholesky factorization per iteration, but you have successful iterations which improve the function being minimized, and you have the unsuccessful one. And in the unsuccessful factorizations, and in the unsuccessful iterations, you do a factorization as well. So as a whole, for improving the objective function, you may need several factorizations. The method we are talking here is a method that at every iteration improves sufficient decrease in the objective function using only one single cheap factorization. So this is the difference. So, well, I already mentioned that. So we would like to employ only one chip factorization per iteration. We would like to preserve the well-known complexity results to achieve first order and second order stationary points. This is what is written here for first order and for second order. And we also would like to have some complexity results for the case in which neither Lipschitz or Holder conditions hold for gradient tangentials. So we would like to have conversions and complexity results even in those cases as well. So the method is strongly based on the idea of mixed factorizations. We have a symmetric matrix here, and we say a mixed factorization is a factorization of this type, MD-MT, where D is diagonal and M is easy. And by easy we mean M is such that solving a linear system with M or N transpose is cheap. Cheap means in the dense case, N square. Okay, so M is such that solving systems with M cost no more than N square in the dense case, and D is diagonal. This is a mixed factorization. Note that in particular the spectral decomposition is a mixed factorization, but we are assuming that computing the spectral decomposition is expensive. So the mixed factorization we would like to use is based on the Bunch-Parlett-Kaufman decomposition. Given H, the Bunch-Parlett-Kaufman decomposition is given by a permutation matrix, lower triangular matrix with unitary diagonal, and this is D here is a block diagonal matrix with blocks of size 1 by 1 or 2 by 2. This is Bunch-Parlett. So, I already said that. So for each 2 by 2 block, you can compute the spectral decomposition, but this is the spectral decomposition of a 2 by 2 matrix. And then this is a 2 by 2 orthogonal matrix, of course. But then you can, let's say, put this in an n-dimensional matrix and plug this into M, and then you have the mixed decomposition, where D now is diagonal, and M is P times L times the 2 by 2 orthogonal matrices, as many as 2 by 2 diagonal blocks in this block diagonal matrix. So the property of this M, since this is the product of a permutation, lower triangular plus simple orthogonal matrices, is that you can solve systems cheaply using this M. And what is the advantage of this mixed factorization? It will be clear in a moment. So this is the main algorithm for unconstrained minimization based on cubic regularization. This is the subproblem we need to solve at each iteration. This is the gradient of the objective function. This is an approximation of the Hessian. This is the regularization term. Note that we are using norm 3 to the power of 3 here. Okay, and all the rest is more or less standard. You try to compute an approximate solution or an exact solution of this cubic regularized model. And if you succeed in the sense that you obtain this sufficient decrease, you are done. Otherwise, you increase the regularization parameter in some way. This is the way in which you increase it, but okay, this is not very relevant at this moment. And okay, so the main step of this unconstrained minimization algorithm is how to solve the cubic regularized model. So here it is the model again. And with this substitution of variables here, y is m transpose times s, g underline is this, then the subproblem is equivalent to this problem, and the property of this problem, which is exactly the same of this one, is that this is completely separable in one-dimensional cubic problems. N one-dimensional cubic problems. So you can solve these problems trivially, solving quadratic equations, and then thanks to the mixed factorization, you have the separability, and then you can obtain the exact solution of the cubic regularized subproblem. So this is the main feature of the method. Okay, so the first theoretical result says that the method is well defined. We need an assumption here. Okay, I'm just phrasing here that H is an approximation of the Hessian at this point. It can be the Hessian, it can be any other thing, and any approximation. We will use the exact Hessian then to recover the well-known optimal results. But at this point, we are trying to prove some kind of complexity result and global conversions without assuming a Holder or even Lipschitz continuity of the Hessians. So for this, we only need this assumption. We need a function satisfying this inequality. And okay, we can obtain this assumption only. Okay, we will use in a moment, in the next slide, that this function exists and is the same for all the iterations. So the existence of this function, a sufficient condition for the existence of this function is the continuity of the first order partial derivatives. And for having the same function for all the iterations, we need the uniform continuity of the first order partial derivative of f. So this is the only assumption we are making here. And with this, the well-defined result is that in a finite number of iterations, we obtain the sufficient decrease we need. So since this is the only inner iteration of the algorithm showing that this can be done in a finite number of iterations, proves the well-definedness of the method. Note that here we are assuming that the gradient is positive for the well-definedness, but this is because we are not assuming that H is the Hessian. If we assume that H is the true Hessian, then we can obtain well-definedness even in the case of a null gradient. So complexity result now. We need some other assumption here. We need the assumption of this upper bound for these quantities. This came from continuity assumptions and properties of the bunch and parallel factorization. This is nothing strong. This is reasonable to assume. Note that we are not assuming boundness of the inverse of the Hessian or even the inverse of the diagonal matrix. And with this assumption, we have that the number of iterations that is needed to obtain, let's say, the number of iterations along which we may have a large gradient or larger than epsilon and an f not below f target is limited by this time a positive quantity that depends on epsilon. Okay, so this gives some kind of complexity result. Of course, this is not the kind of complexity result. I'm not showing the expression here. It's not the usual ones because, as I said, we are not assuming Holder or Lipschitz continuity of the Hessians. So this is a complexity result, but not in the sense of the optimal one. Of course, as a corollary of this theorem, we have that all the function is unbounded below, and we have the conversions of the norm of the gradient in Lim-Inf. However, with a small modification in the way we update the regularization parameter. I didn't mention how we do that. It's in the algorithm here in the usual way. Note that at every iteration we start with this sigma big is something that we initialized, but it's increased or maybe increased at every iteration. So this sigma big is not an upper bound on the initial sigma at every iteration. So we may have that along the iterations, we start with a larger and larger regularization parameter, although it appears here that it's limited. It is not, because sigma bit is not a constant. It's being updated. And this is why we obtain the lim_inf for the gradient. However, if you include a new parameter for the algorithm and you ask for the first regularization parameter at every iteration to be safeguarded in this way, then you obtain the lim. So this is something technical of the algorithm, but you can obtain both depending on this detail, implementation detail. And moreover, we obtain with the usual assumptions, we obtain the usual optimal complexity results for first order and second order stationary points. Okay, this is not new, this is well known. So this is a comparison. We are considering, note that here we are substituting something that could be the spectral decomposition, but something that is based on Bancham-Parlett decomposition. So there are some stability issues involved in this kind of decomposition. So in this experiment, we consider only dense decompositions, and we were trying to assess whether using a less stable decomposition, because Bancham-Parlett has different kind of pivoting strategies, the ones that work well in practice has not the same stability results of the spectral decomposition. So here we were trying to assess that using the Bancham-Parlett based mixed decomposition, which is the green one here, is as robust as computing the spectral decomposition, but is much faster, at least for this set of problems from the QTS collection that we are taking from the same paper that Sandra presented about the algebraic rules for solving nonlinear least square problems. Those are the same problems we took from there. There are all the problems for the QTS collection with second order derivatives or something like that. And in this second experiment, we are comparing this approach for unconstrained minimization against the well-known ARC method. We took the results of the ARC with the G rule. ARC with the G rule is the there are three different strategies in the paper where the ARC method is presented, and this one is the one with the best results from there. And we are comparing only number of function evaluations because this is what it was available in that paper. And here we are showing that, recall that in the ARC method, subproblems are solved iteratively. And here we are using only one chip factorization per iteration, so it is expected our method to be faster than the ARC method. And in any case, they use mostly the same number of functional evaluations. So this is a good result in the sense of showing the robustness of the approach. Okay, so now let's partial conclusions. I guess it's more or less clear. We develop a method for unconstrained minimization with cubic regularization. It's practical in the sense that it uses only one single chip factorization per iteration that gives sufficient decrease. It enjoys convergence results and complexity results when we are not assuming Lipschitz or Holder conditions on the Hessians. It recovers the well-known optimal complexity results when those assumptions are included. And we have numerical experiments showing that it works well in practice. So this is, let's say, a practical algorithm for unconstrained minimization based on complexity results. So let's go to the second part of the talk. This is the classical Powell, Hestenes, Rockefeller augmented Lagrangian method, function, sorry, and here is the method. This is Algencan. At each iteration, we solve approximately this bound constraint minimization problem. We update the Lagrange multipliers. This is the safeguarded version that Mario mentioned yesterday. And, depending on some inequalities, we update the penalty parameter or not. And this is the safeguarding of the Lagrange multipliers, and we iterate. So I will skip this part because I'm running out of time. This is a description of the theoretical asymptotic conversion results of Algencan. It's well known at this point, I guess. So these are the complexity results of Algencan. Note that Algencan was not developed to obtain or to possess nice complexity results. Algencan, it is what it is. And we were trying to compute the complexity that Algencan possesses. With the expectation of, that knowing Algencan better can take us to the way of improving it. So what we have here, we have two different kinds of complexity results. In the first case, we assume boundness of the penalty parameter, yes? And assuming this, we have that basically we will have conversions to a feasible point, and this is the number of iterations until reaching a point that approximately satisfies the KKT conditions. So delta is the precision, the tolerance for feasibility and complementarity. Epsilon is the tolerance for optimality. This is a problem-dependent constant. This is the way we update the penalty parameter. And this is some other constant that appears. Okay, this is the way we update the penalty parameter, and this is a fraction that appears. And we say that the penalty parameter is updated if this fraction of feasibility, if the feasibility does not improve at least this function. So you can see here that, note that here we are using the sequence epsilon k, which is usually provided. So the number of iterations n epsilon is the number of iterations required to have epsilon k below epsilon. And this can be order 1 because you can use epsilon since the beginning, since iteration 1. So this is mostly a constant. And this is the way in which the number of iterations depends on delta. And you can see that it appears a logarithm here. So let's say that if this is the number of outer iterations of the augmented Lagrangian method, roughly speaking, the complexity of the augmented Lagrangian method is given by the complexity of the method for solving the subproblems, roughly speaking. And this is the upper bound for the penalty parameters. Here is the result where we assume that we have a method with complexity results for solving the subproblems. And if we have a method for solving the subproblems with complexity results, and this is the complexity of the inner solver, so roughly speaking, you multiply the complexity of the inner solver by the number of iterations. You have the for solving each subproblem, it appears epsilon k here to this power and multiply by this constant, and then you replace the epsilon k by the minimum and multiply by the number of iterations, and you have the complexity of the whole method. And this is now without the assumption on the limitation of the penalty parameter. And then, so you have two possible outputs, or you may find, as Mario said yesterday, a point that is stationary of the infeasibility measure, but it's infeasible. So this means that the point is infeasible, but at the same time it's stationary for the infeasibility measure. So this is one possible output. This is the other possible output, which is approximately KKT. And this is the number of iterations you should wait without the assumption of the penalty parameter boundness to obtain an iterate satisfying 1 or 2. So once again, with the assumption in which you have an inner solver that takes this number of iterations for solving the subproblem. Note that here it appears rho k, which is not bounded anymore. Here we have epsilon k, so this is the complexity for solving the subproblem. And so then you replace rho k for the maximum and epsilon k for the minimum. There is an expression for rho max given somewhere. Well, given before means given before in the paper. But it's a constant. And then you have that this is the whole complexity of the augmented Lagrangian method. Okay. So we are up to this point. I introduced an unconstrained minimization solver with complexity results. I showed the complexity of the augmented Lagrangian method, and I would like to talk now in the last 3 minutes, because Alfredo talked a lot at the beginning.
But you can have 5 minutes extra.
Okay. Okay, thank you very much. Okay, thank you. So now we arrive to the point where I would like to show you the implications of the complexity results in the practical performance of AlGenCAN. So the first step is embedded the unconstrained minimization solver in a bound constrained minimization solver. By doing that, you preserve the complexity result. This is what I talked in the last Brassopt. Of course, there is a paper written about that, but I will skip it here. We made a comparison of this bound constraint minimization solver with the Newtonian bound constraint minimization solver of AlGenCAN, which is known as GenCAN for the ones that are familiar with that. So we compare GenCAN, which is a line search Newton method, against this method with complexity results. They both work more or less the same for small problems. But in fact, this comparison pointed out not to good qualities of the new method, but to bad qualities of the implementation of GenCAN. And one of the points is that when you are trying to solve a cubic regularized subproblem, you have the quadratic model of the function plus the regularization term. The quadratic model of the function lies in the dimension, let's say the unit of measure of the quadratic model is the unit of measure of the image of the function, while the regularization term lives in the domain. So the penalty parameter, the regularization parameter, or the initial regularization parameter plays a very important role in the sense that you are summing together something of different magnitudes. When we implemented this kind of method with cubic regularization, we pay a lot of attention in the way we should define the initial regularization parameter to make sense in some way. But when we implemented the GenCAN, the Newton line search, we didn't care about that. So that was one of the differences of having good performance in the cubic regularization method and not in GenCAN. So this was at least one of the indirect ways of improving AlGenCAN, taking care of the same things that we realized when implementing the cubic regularization method, and including these improvements in GenCAN. The other point is this one. When you are trying to solve a cubic regularization subproblem, or a bound constraint minimization problem using these cubic regularization strategies, you need to compute, this is the Hessian of the augmented Lagrangian. At each subproblem, you are minimizing the augmented Lagrangian subject to bound constraints. So you have this Hessian, and you need to compute the factorization, the mixed factorization of this Hessian. So for computing the mixed factorization, well, you need to start computing the Hessian. And computing the Hessian may be very expensive. Note that here you have the Hessian of the objective function, the Hessian of the constraints, and the first order terms here with the Jacobian of the constraints. Here, equality constraints, and the Jacobian of the inequality constraints here. And the problem with this Hessian of the augmented Lagrangian is that even though the Hessians of the objective function and the constraints are sparse, the Hessian of the augmented Lagrangian may be dense. So computing it may be not affordable, or maybe decomposing it may be not affordable. In the context of a Newtonian method with line search, solving the Newtonian system with this Hessian can be replaced by solving an augmented linear system in which this is the matrix of coefficients. And the property of this matrix of coefficients is that here you have the Hessian of the Lagrangian, which preserves the sparsity of the Hessian of the objective function and the Hessian of the constraints. And here you have the Jacobian of the constraints, or a subset of the gradients of the constraints, that also preserve the sparsity of the Jacobian of the constraints. So this matrix preserves the sparsity, while this one may not. In the mixed factorization approach, there is no alternative to this. In the Newton with large search, there is one, and this is the alternative. So in large scale problems, or in problems with dense Hessian of the augmented Lagrangians, this alternative would be preferable. In Algencan or in Gencan, both alternatives were present, were options, but choosing between this or this was up to the user. How can the user know from the beginning whether he should use this or this? The decision is not simple. So what we included at that point is a dynamic and automatic selection of one of the two approaches. So we start computing this Hessian, and if the Hessian becomes dense, we switch to this one. So for small problems, this one may be. Imagine that you have a problem with one variable and 1,000 constraints. This is a system of 1 by 1, and this is a system of 1,000 by 1,000. So in that case, this one would be better. So there are some rules that can be used to automatically choose between one or the other. Finally, revisiting the augmented Lagrangian approach, there is something called acceleration step. In the acceleration step, you try to solve the KKT system in between the augmented Lagrangian iterations. In the previous version of Algencan, this KKT system used square slack variables to reformulate inequality constraints, because we would like to have a nonlinear system of equations. Here we are using a semi-smooth approach where we use the mean function for the inequalities and the complementarity constraints. So this is also something different between the previous version and the new version of Algencan. And since I'm running out of time, I will not answer to this question, what do we do if the system is solved? Because if you solve this system, you may find a maximizer on an unexpected or undesirable stationary point. So I will leave this question for some other day. So these are the numerical experiments. We consider all problems from the QTest collection, all of them. Those are some characteristics of the problems. There are unconstrained problems, bound constraint problems, feasibility problems, nonlinear programming problems. This is the maximum number of variables, and this is a kind of distribution of the other problems with respect to the maximum number of variables. Okay, so this is a first comparison. We solve all these problems using Algencan and using IPOpt. In Algencan, bound constraints are satisfied at every iterate, and of course at the solution as well, unless the last iterate is an acceleration step. if the last iteration is an acceleration step, you have here the bound constraints, and this bound constraint may be satisfied with tolerance up to the -8, because this is the stopping criterion for solving the Newtonian system, KKT system. So in Algenkan, the bound constraints are always satisfied with full precision or 10 to the -8. Are never violated by more than this. In IPOPT, which is an interior point technique, bound constraints may be violated. And so this picture shows the number of problems, and we solved with both solvers, and then we checked whether the bound constraints were being satisfied or not. And here is the precision. I wasn't able to write this here. This is 0, 10 to the -1, 10 to the -2, 10 to the -3, and 10 to the -16, and 0. And you can see that independently of the required precision for the bound constraints, Algenkan almost always satisfies the bound constraints with full precision, when in IPOPT there is a decrease here. So there are less problems being solved with precision 10 to the -5, 10 to the -6, 10 to the -7, and if you regard precision larger than 10 to the -8, no more than 800 problems are being solved. So in this sense, Algenkan preserves feasibility of the bound constraints more frequently than IPOPT. Then we fixed the satisfaction of the bound constraints and the other nonlinear constraints. So all nonlinear constraints are satisfied with this precision. Bound constraints are satisfied with this precision. There are 700 problems left. And then we compare the objective function obtained by one solver and the other solver. And here you can okay, this is the distance to the best of the two values. And you can see that in almost all cases, Algenkan finds better functional values than the functional values found by IPOPT. This is the amount of problems in which one of the methods found a solution if the tolerance in the objective function is 10 to the -3, 10 to the -4, and so on. So Algenkan finds more feasible points, finds better functional values. And finally, we compare CPU time. In green, you have IPOPT. So this is CPU time in the cases in which both methods found the same solution. And you can see that IPOPT is a little bit more faster than Algenkan, but they are mostly the same. So they use the same time for finding solutions in case that both methods found the solution. Conclusions, we have a new version of Algenkan. The improvements in Algenkan were based on new results, on complexity results in some sense. Algenkan has a modular approach, and we show in this presentation in which way this modularity can be used to easily improve the performance of the augmented Lagrangian method. And those are the reference related to the presentation. So thank you very much.